Recording.
Okay, today it's a pleasure to me introduce Professor Caulfield. I'll just talk a little bit about Professor Caulfield. Caulfield is a professor in University of Cambridge. Okay, Professor Caulfield is internationally recognized for his contribution to fluid mechanics, particularly in the study of instability, transition to turbulence, and mixes in Stratified flows, with important applications to ocean heat, transport, and climate science. Also, Professor Caulfield is editor-in-chief at the Journal of Fluid Mechanics and co-director of Cambridge Institute of Computing for Climate Science. Today is a pleasure, Professor, to accept to give this talk. And Professor Caulfield will talk about transition in Stratified Shear Flows. Thank you, Professor. You can start.
Okay, thank you very much, Roberto, for that very kind introduction. And also thank you to the organizer of this seminar for this invitation. I'm always delighted to talk about the research that I have been involved in. So today, as was said, I will be talking about transition in stratified shear flow. Hopefully, I will get to the very exciting new results of Philip Vuig, postdoc who worked with me for a couple of years in Cambridge, supported by the German research funding agency DFG on the Walter Benjamin program. And also, I'll hopefully be able to explain these pretty videos and also highlight some of the history of the previous great men who worked on this problem for over a century. This has been a problem of interest, and these four here are Lewis Fry Richardson, G.I. Taylor, my real hero, John Miles from UC San Diego, and Lou Howard, who was at MIT and other places over time. So in the next 40 minutes, what will I try and do? I'll try and explain to you why this problem is important and highlight these different conjectures and a theorem. So why should we care about stratified turbulence? Well, we all know that the global climate system is being modified by human activity, but what is not so well known is that the vast majority of the increased amount of heat that is going into the global climate system is going into the ocean. This is a beautiful paper from 2023 that summarizes all the available data and shows that of the total heat gain measured in the order of hundreds of zettajoules, i.e. 10 to the 23 joules, nearly 90% of that heat has gone into the ocean, and only 2% of it has gone into the atmosphere. And in particular, nearly 40% of the heat has actually gone into the deep ocean at depths below 700 meters. And this is really shows you that understanding how heat is transported in the ocean is central to understanding the global climate system. One further way to reinforce that, if you think of the entire atmosphere all the way up to what's called the Kármán line, which is where the atmosphere is so thin that you can't fly, there's not enough lift, you basically orbit. If you take a column of air the whole way up to that height, and raise it by 1 degree, what amount of heat you need to raise the temperature of that column of air by 1 degree centigrade, that amount of heat is the amount of heat that you would need to raise a column of water of only 3.4 meters depth of the same cross-sectional area by 1 degree. The heat capacity of the ocean is vastly larger. Remember, 70% of the world's surface is covered in ocean, which is on average 4 kilometers deep. So understanding how heat is transported in the ocean is central to our understanding the global climate system. And what is so you have these there's this well-known kind of conveyor belt of typically transporting heat poleward, though in the Atlantic it's all northward. Here is a plot of the heat transport positive being towards the north in the various ocean basins. And you'll see the heat transport is measured in petawatts. It's 10 to the 15 watts. And typically for the Pacific, it is northward in the northern hemisphere and southward in the southern hemisphere. And since you were bringing hot water from near the equator towards the poles, you then have to have some return flow that is caused at the polar regions where cold water sinks to the bottom and then compensates for the conservation of mass. If you have surface currents going towards the poles, you have to have some water coming in underneath. But that would just mean, if you're simple-minded, you'd have a layer of very hot water at the top and colder water underneath, and that is not what's observed. If you measure the ocean stratification, so if you measure the density variation with depth, you find that it is quite a continuous variation with depth, and it's more dense near the bottom and less dense higher up. And this is quantified in terms of this dynamically significant quantity called the buoyancy frequency, because the buoyancy frequency, if you have dense fluid low down and less dense fluid higher up, if you lift the dense parcel up, that will there is a restoring force, obviously, and so the dense parcel will want to fall down. And when it falls down, it converts potential energy into kinetic energy, and then when it reaches its equilibrium position, it overshoots, and so it goes deeper, and so there's a natural frequency of oscillation in the system called the buoyancy frequency. And these are measurements in the South Atlantic off Argentina, actually, and this shows that this frequency in terms of cycles per hour is about 1 cycle per hour. That's the period of these oscillations, and it's pretty constant. There's variation near the surface due to the wind, but then you see there's a regular variation with depth all the way down to the bottom of the ocean there, which is since it's off Argentina, it's still in a shelf. It's about 1.5 kilometers deep. So how have you got this? Well, the only way you've got that is you've got to have some mixing, some turbulent mixing, lifting cold water up or equivalently bringing hot water down to lead to this continuous profile. And understanding that turbulence is a central uncertain way to improve the modeling of the climate system. It's one of the big uncertainties in it, and it's the thing that connects to the fluid mechanics problems that I'm interested in. And here's a flow visualization of the sort of dynamics that you might have done by one of my PhD students, Chris Howland. What we have here is a triply periodic box where we have a constant buoyancy frequency, a constant gradient in density, and we have a velocity shear. But to make it periodic, it's this sign. We have it as a sine. And what we see in this case is the top plots is the flow vorticity, the swirl, and the bottom plot is the buoyancy. And what we have here is one of those. I mentioned that this buoyancy frequency means you can have oscillations, so the oceans are full of internal waves that are propagating at some angle, but when those waves interact with the shear, they break and they undergo these sort of turbulent events, and we try and want to understand how does the interaction between velocity shear and these kind of internal waves, how does that behave in an idealized situation to be able to understand it properly? And fundamentally, the key concept is to understand how the turbulence changes, how turbulence might change the density distribution. So here's if you have the blue line represents the gradient in density, and you have some turbulence, the question is what happens? Do you get something that looks that does the background gradient not change at all, the turbulence not affect the stratification at all, or does it completely mix it up, or does it do something in between? And if you think about the completely mixed up case, you would say, well, if I think about the potential energy of this system and then look at the potential energy of this one, I appear to have I've on average lifted dense parcels up, so I've increased the potential energy. So there's then a real issue you need to think about. How does the kinetic energy in the shear compete against the potential energy requirement to lift parcels up? And a classic bulk measure of this is Richardson came up with this idea that there's a key parameter here, and so they're called Richardson numbers. And so if you think about here, we have just an idealized velocity profile u and an idealized density profile rho. If you think about the potential energy I'd need to do to mix this up with this characteristic jump rho naught, that's a sort of measure of the potential energy I'd have to do. But the kinetic energy embedded in that background shear, this is ignore factors of 2 and so on at the moment, but that's a measure of the potential energy, the kinetic energy if you talk about per unit volume. Now, so it seems plausible that if this parameter is large, there's not enough kinetic energy to trigger turbulence. Whereas on the other hand, if it is small, there's plenty of kinetic energy to trigger turbulence, and so it can mix things up. And so that is a kind of bulk measure. But the further important point is you can think about local measures of the relative importance of stratification and shear in terms of a ratio of timescales. Now, I've already introduced this buoyancy frequency, which is associated with the background gradient in density. But of course, if I have velocity shear, then that velocity shear has a characteristic timescale in it associated with how much vorticity is in it, basically. It's the velocity shear in the background has some, is an inverse timescale. So once again, if this gradient Richardson number is small, we think there is enough kinetic energy in the shear to drive a mixing event. Whereas conversely, if it's large, it seems plausible that we wouldn't have enough kinetic energy. And the beautiful work of Miles and Howard was actually to formalize this in terms of a theorem. And of course, I'll just give you an impressionistic mention of this theorem. I know this is a seminar to do with PDEs. So here are the two key PDEs in this particular situation. This is the stratified Navier-Stokes equation. So we have the local variation of velocity, the local acceleration, the advective term u dot grad u. Then on the forces on the other side, there's going to be a perturbation pressure. There's going to be a buoyancy force. This is the rho primed is the density variation away from a constant gradient in density. It's like a perturbation quantity. So if locally the density is large, you will tend to accelerate downwards. Conversely, if locally the density is small, you will tend to accelerate upwards like a hot air balloon. And so that term's quantified. And then you have viscosity, and you suppose the fluid is solenoidal, so that the velocity field is divergence free. There's a subtlety to do with the possible diffusion of the density field if we have a single component, like we've just supposed the density varies with temperature. These are called the Boussinesq equations. But if we go to the very simple situation where we ignore the effects of viscosity and diffusion of the density and do a classic linearization approach, so we suppose there's a background velocity shear, there's a background pressure, there's a background density gradient, and then we fluctuate away from them, and then suppose that all these fluctuation perturbation quantities are small and smooth, so we can do a linearized Fourier decomposition. So we suppose that all the terms have some eigenfunction in Z, and then they are wave-like in X and C. We're interested in whether the perturbations can grow without time. And so within this expression, that corresponds to the phase velocity C having an imaginary part. And if we linearize these equations and eliminate all the terms except the vertical velocity, we end up with this equation, which is called the Taylor-Goldstein equation after G.I. Taylor and Sidney Goldstein, which is the stratified variant of the Rayleigh equation for the stability of shear flow, of inviscid shear flows. You have this extra term, which involves the buoyancy frequency. And you'll notice this is it's a complicated ODE, but it's with a regular singular point at when the phase speed, if this phase speed is purely real, and at a point where the background velocity is the same as the phase speed. Now, the brilliant insight of Howard was to do the following transformation. He put in, he considered the variable h, which was w divided by the square root of u minus c, And then through a manipulation, he was able to end up with this very elegant manipulation. He was able to end up with this particular condition that had to be satisfied. So this quantity has to be zero. This is the integral over the depth of the domain of these 1, 2, 3 different terms, pre-multiplied outside, crucially, by CI, the imaginary part of the phase speed. Now, remember I said that we wanted, for an instability, a normal mode instability, we have to have CI not being equal to 0. And so for there to be any chance of an instability, we need the term in the square bracket to be 0. But now let's think of each of the terms in the integrand. This term here is clearly positive definite. This term here, if we suppose the wave number is real, if we look at temporal instabilities, this term here is positive definite. This is positive definite. This is positive definite. And so the only way we can have an instability is if somewhere the term in this bracket is negative, because that's the only possible way we could cancel out. And this is a statement, a rigorous statement about the properties of the stratification of the buoyancy frequency compared to the shear. You have to have, for an instability, so if Ci to be not equal to 0, and yet the term in the square bracket to be 0, you need n squared to be minus 1/4 du bar dz, the quarter turns up, has got to be less than 0 somewhere. But this is equivalent to saying the gradient Richardson number has to be less than 1/4 somewhere. And so there is a sufficient condition for stability is that the Richardson number is greater than 1/4 everywhere. Now, crucially, I must stress this is a sufficient condition for stability. If you have a low Richardson number, you don't necessarily have instability, but you can have instability if the Richardson number is small anywhere in the flow. And so even if you have a region where the Richardson number is large, if it is neighbored by somewhere that is small, then all bets are off. Why do I highlight this point? Well, there is an interesting further detail that this is really a statement about how the relative length scales of the velocity variation, which is shown in blue, to the variations in density, which is shown in red. If both of them have local variation, the region over which they vary is about the same in scale, then you have the Richardson number is minimum at the midpoint of the shear layer and then increases away. So if the midpoint of the shear layer is greater than 1/4, then you're definitely stable. But alternatively, if you have what's called a sharper density interface, which is, you see, the region over which the density varies is quite narrow compared to the region over which the velocity varies, then even though the gradient Richardson number is very large at the interface, it drops to small values either side. And so the Miles-Howard theorem doesn't apply. Now, these are plots of hyperbolic tangents, and the reason that we use why do we use hyperbolic tangents is because when you use hyperbolic tangents, you can get an analytical expression for the neutral curve of solution to that Taylor-Goldstein equation, which is shown here. This was actually there were numerical calculations 50 years ago now of the over 50 years of the growth rates for values below this critical curve. But the critical curve takes a really elegant form. It is just in terms of the non-dimensional wave number alpha 1 minus alpha, which naturally has its maximum value at 1/4, which is precisely when the theorem says that it should be marginally stable. But conversely, if you have a sharp interface like this case, so for values less than minimum Richardson number less than 1/4, you can have instabilities, and they grow into the classic Kelvin-Helmholtz instability, the sort of thing that's shown here. That's what I'm going to mainly be talking about in this talk. But I also do want to mention these sharp interface conditions, because when you have the sharp interfaces, you can have a different type of instability, which is called the Holmboe instability. But we're not really going to be talking about that here. So I've shown you the theorem. And now we can understand this video from before. This is a tilting tank apparatus. We have fresh water at the top, salty water at the bottom. We let it tilt. The fresh water runs up, the salty water runs down, and you get a roll up into these beautiful Kelvin-Helmholtz billows entirely consistent with the theorem. And this is just a false color to show you that these cause a lot of mixing. You see, you started off with a thin layer of green, but they mix a lot and you get much more green as it rolls up. Now, these you can numerically simulate, but you also see these very if you know what you're looking for, you very frequently see these billow trains in the atmosphere. This is a photograph in Canada. And you also actually can measure them in the ocean. A tour de force observation in the Romanche Trench, which is in equatorial Atlantic, of measurements. You see, this is in meters. These are 4 kilometer down measurements, and you see these amazing trains of billows. This is a zoom up of that particular region, but you see they saw at one particular site, they saw hundreds of these overturnings that look exactly like those sort of numerical simulations. So these phenomena actually do exist in the world's oceans. But we have a condition when they definitely don't exist. The question is, when do they exist? And so if you look at a viscous version of the Taylor-Goldstein equation, which is, you could call it a stratified or Sommerfeld equation, or a viscous Taylor-Goldstein equation, and you look at pretty high Reynolds numbers for the flow, and you then vary the Richardson number, this minimum Richardson number, at which the instability should take off. And you look at how much the energy from the background flow you end up in the billow. You find that for no stratification at all, about a third of the energy in the background shear is extracted from by the overturning billow, and this happens in terms of non-dimensional time units, the advective time units given by the characteristic u and the characteristic depth d, in about 30 of those time units. These billows typically roll up quite quickly, and then as you increase the stratification, more of the energy goes into the potential energy of the system. The billows decay in their intensity somewhat, but then something very different happens when the bulk Richardson number gets over about 0.1, 0.15. You'll see up to there, the potential energy is increasing, and the amount of energy that has been extracted from the main flow doesn't vary much, but then it starts to really rapidly drop. And the time at which the billow rolls up starts to diverge towards infinity. And so in particular, if the minimum Richardson number is close to the critical value, i.e. a quarter, then the growth rate is very small, but also the maximum amplitude is very small. And the time at which this maximum amplitude occurs is diverging towards infinity. And so the real question that I'm interested in, where we're going to come to the conjectures, the theorem tells us that for Richardson number greater than a quarter, you can't have instability. But what I really want to know is, what is the Richardson number at which we can have significant turbulence to do the mixing that matters for the world's oceans and the atmosphere? And it suggests that if you're very close to a quarter, this billow can't really roll up strongly. Okay, that's great. But then you might say, well, we're only looking at linear normal modes. What about transient growth? Because we have a background shear here, the operator is not self-adjoint. So the classic sort of idea we know from even if you have two, if it's not self-adjoint, the eigenvectors or in infinite dimensions, the eigenfunctions are not orthogonal with respect to the norm. And so even if both of the eigenfunctions decay with time, as shown here by phi2 and phi1, they both decay with time, their sum f can actually transiently increase because of non-normal growth. So you might say, I just say you can't have linear instability, but could you have transient growth? Well, we did a calculation with Alexis Kaminsky, who's now a professor at Berkeley. And we found there was transient growth that kind of looked like a Kelvin-Helmholtz billow in flows at quite high Reynolds numbers for maximum Richardson number greater than 0.4, but their amplitude was really weak. So that couldn't possibly be the explanation of what was going on. So we need to explore further. So we now have a bit of a conundrum, right? we have, oh, I wanted this video to work, but it's not. Oh, there it is. Yeah. So we have a bit of a conundrum. We have that the linear instability saturates at, the linear instability has zero growth rate at a quarter, but it has the growth rate increase as you reduce the Richardson number. And we have these vigorous mixing events like these Kelvin-Helmholtz billows. And so the question we want to answer is at what minimum Richardson number is likely to be the minimum Richardson number that causes the significant mixing events in these flows. And that's what I'm going to try and talk about in the next 15, 20 minutes. And the reason that, and the question I'm going to ask is the question that I always ask in fluid mechanics, and is the question that every fluid mechanics person should ask, is what would GI do? And what would G.I. Taylor do to address this question? And as I said, the equation is actually named after G.I. Taylor, the Taylor-Goldstein equation, but that was only published in 1931, even though he had worked on it in earlier. And so what I'm going to, this is his famous research group in 1955 in Cambridge, and I'm going to highlight the great work that was done by two people there. This is Tom Ellison here, and this is Stuart Turner, who's actually my academic grandfather, the supervisor of my supervisor. And they did some great work in the 50s that really does resonate down the ages. So, and that's G.I. Taylor in the middle, and he had considered this problem. And as I said, he worked out the equation, and it's got this very interesting first paragraph of the paper he published in 1931, saying the chief part of the work described in this paper was done in 1914 and formed part of the essay for which the Adams Prize was awarded in 1915. During the war years, it was laid aside, and since then I have delayed publication, hoping to be able to undertake experiments designed to verify or otherwise the results. Effectively, he was trying to find the minimum, this neutral behavior, and it just wasn't behaving as he was expected. Lately, however, he became aware that the equation had been independently derived by Sidney Goldstein, and so they published the two papers back to back in the Proceedings of the Royal Society, just giving equal credit to the two people who had derived the equation. But so this is the smoking gun that the experiments were hard to do. And fundamentally, as I mentioned, because we're interested in heat transport, we're really interested, going back to this picture, we're interested in how much mixing occurs and how much increase in potential energy occurs for a stratified shear flow. And this, I use the metaphor, the analogy, that this is really, you want to understand how stratification taxes turbulence. Because if you look at the equation for turbulent kinetic energy, you have the local rate of change of it, there's some divergence of a flux. In a shear flow, there is a production term extracting energy from the background shear. I've already alluded to that. And then you have classically the viscous dissipation, this term, which is you are converting kinetic energy into internal energy. But if you have a stratified fluid, you have this extra term, this lifting up of dense parcels. If on average you're lifting dense parcels up, you convert kinetic energy into potential energy, and so therefore there is a tax on the turbulence that's going on if it remains reversible. This is equivalent in engineering terms to working out an eddy diffusivity for the heat. This is this buoyancy term, this density flux, compared to the background gradient. You know, this is a classical gradient flux argument, right? That you suppose, how does this buoyancy flux, can I describe it in terms of gradients of mean quantities, which gives us that particular thing. Now, this is relatively well known. I mean, I know most of the people in this audience are not necessarily fluid dynamicists, and certainly looking at turbulence, but the derivation of the turbulent kinetic energy equation is well known. But when you have a stratified fluid, you actually can do an analogous thing for second order autocorrelations of fluctuation quantities in terms of the buoyancy variance. Remember, I said rho primed is the deviation away from this background gradient. And when you scale it with these prefactors, this quantity has exactly the same dimensions as this energy density. And interestingly, when you do that, you have time-dependent term, you have a divergence of flux, and you have precisely the opposite term. This buoyancy flux is now positive. So if you're on average, your lifting dense parcels up, you're increasing the buoyancy variance, and you crucially have a destruction term, which knows about the diffusivity of the heat of this variable, which is sign definite, which is very, very similar to the dissipation rate. And so really, you want to understand the ratio of this quantity chi to the dissipation rate epsilon, and this is quantified in terms of this parameter that's called gamma. Now, I'll briefly say that though I presented this as an equation of buoyancy variance, you actually, if these fluctuations are deviations away from a constant background gradient, this is actually an equation for available potential energy, the component of the potential energy that can go into be put back into fluid motions. And so you are now able to separate the kind of reversible part of the dynamics, which would be an oscillating wave. Let's say it lifts dense parcels up and puts parcels down. You don't have any mixing in that. You just have an oscillation. But if you have small scale motions and you irreversibly change the properties of the fluid, you must have mixing, and that is quantified by this. So you can understand it in terms of destruction in variations in the local variations in the density, because obviously a mixed fluid has the same density everywhere, so you have destroyed the buoyancy variance, but also in terms of the energy reservoirs between available and potential energy reservoirs. So there we are. Now start on the conjectures. The first conjecture is really that sustained sheared stratified turbulence is weakly stratified in the very specific sense that the eddy diffusivity, the turbulent Prandtl number, i.e. the ratio of this eddy diffusivity of density to the eddy diffusivity for momentum, the turbulent viscosity, is 1. And that is then said, that's what it means by weakly stratified, that it is a fluid, that the density variations are mixed up exactly as you mix up the momentum. And the fact of this energetic cost, or the fact that potential energy matters, doesn't play a key role. And indeed, this dates back, there's a deeply important paper due to Tom Osborne that kind of has this argument that the quantity gamma is bounded above by 0.2, and that naturally arises from an argument that the turbulent Prandtl number is of order 1, and that you can only have mixed because the turbulent Prandtl number, this ratio, can be written as n squared over s squared, the gradient Richardson number, compared to what's called the flux Richardson number, which is the buoyancy flux divided by the production, which can be related to gamma. It's in this particular way. And importantly, the value of 0.2 suggests that this flux Richardson number should be less than 1/6. That's just you plug in the numbers. And if you have the turbulent Prandtl number is 1, that says the gradient Richardson number isn't 0.25, but is at most a sixth, about 0.15. And this is a key thing that is kind of this conjecture. So can we test this conjecture? Well, one way you can do it is by looking at large numerical simulations. And we looked at a very simple case, which called stratified plane couette flow. So you have a hot plate at the top, a cold plate at the bottom, that are moving at relative velocities. And so you have a natural way to define the gradient Richardson number here in terms of the conductive state, that you have a linear gradient in density and linear gradients in velocity. And you see if you can get this flow to be turbulent for different values of the Prandtl number. And amazingly, you find that the flux Richardson number against the characteristic gradient Richardson number in this flow follows very, very closely this 1 linear relationship, i.e. that the turbulent Prandtl number is precisely 1 until you get up to about 0.15 or so, and then you can't sustain turbulence, 0.2. It's definitely not a quarter. It is markedly less than the classic critical value. And for larger Richardson numbers, spatial intermittency is inevitable. You see this sort of banding structure here where you have turbulence and then no turbulence. This is measured near the top wall. And you see here the images of entropy, i.e. the square of the vorticity. You have regions where it's large and then regions where it's really quite low. And as you vary the Reynolds number, force the flow harder and harder, even all the way up to like 300,000, you can't sustain turbulence for Richardson number much bigger than about 0.2. And the flow inevitably laminarizes for larger values. Okay, so there's a similarity theory we can have in this particular case where we can construct a model basically saying in this situation, you have if you actually have turbulence and you have a hot plate at the top and a cold plate at the bottom, you can have if it's turbulent, you will have a constant flux of heat or buoyancy through the system. And so you can construct a theory saying that everything depends, that you have a similarity theory where everything depends on this Molin-Oberkopf length, which is a relationship basically between the flux of the vertical buoyancy flux, this denominator here is B, and the friction velocity given by the wall shear stress, how much momentum you're putting into the system. And you construct that theory and you find that you can't sustain turbulence beyond about 0.2, and all our data really agrees with this theory. And once again, as I said, even when the Reynolds numbers go up to very, very large values. So this leads me to conjecture 2, that sustained sheared stratified turbulence has a Richardson number that is less than a quarter as Reynolds goes up to infinity. And this was actually postulated by Tom Ellison 70 years ago. He was saying that the flux form of the Richardson number cannot exceed a critical value, which is about 0.15. And once again, turbulent Prandtl number, flux Richardson number, same as the gradient Richardson number, so it's about 0.15. That's what he postulated. So sustained turbulence has a critical Richardson number that is strictly bounded away from the linear stability value as Reynolds number goes towards infinity. And so how can we test that? Well, I'm presenting it as this was what we planned to do. How we tested that was in this idealized simulation. You have a constant, you set up your system to have a constant velocity gradient and a constant density gradient. And so then you only calculate the perturbations away from that state. And the perturbations away from that state, you then satisfy this combination of equations, which have control parameters, the Prandtl number, the ratio, the diffusivities, a Reynolds number, and the Richardson number, which couples the density fluctuations into the velocity fluctuation equation. And so what we did in this case was an interesting control problem. What we did was we said, okay, we're going to want to have a target amount of turbulence given by the turbulent kinetic energy, and we're going to choose whatever that is, and then at a Reynolds number. And then if that target amount of turbulence decreases, that says the stratification is so strong, so we reduce the Richardson number. It's like changing gravity. On the other hand, if the kinetic energy decreases rather, that means that the stratification is too strong. Sorry, I'm doing this backwards. If the stratification is too strong, the kinetic energy is dropping, so we reduce the Richardson number. If, on the other hand, the kinetic energy is increasing, the stratification is too weak, so we turn up the Richardson number and we wait until it equilibrates. And so for that flow, it will emerge what the dissipation rate is, what the mixing is, and what the Richardson number is when it's steady. But remember, we're varying Reynolds numbers and turbulent kinetic energy to try different values. And so here's the sort of situation that happens. When the Reynolds number is relatively small, quantified in terms of this buoyancy Reynolds number, you see the density fluctuations look like this. As you increase the Reynolds number, you see greater range of scales, higher dynamic range. That's what you'd expect. That's what the density field looks like. But what do these parameters look like? Well, the flow converges to state across a huge range of Reynolds numbers, by a factor of 30, converges to a state where the turbulent Prandtl number is 1, where gamma is almost precisely 0.2, and yet the Richardson number is, again, this 0.15, 0.16, strictly smaller than a quarter. So this really suggests that that Ellison was onto something. So what was the third conjecture? The third conjecture that I want to talk about is in Stuart Turner's book on buoyancy effects in fluids. And what he conjectured there was that the flow is in a kind of equilibrium. So the flow, this critical Richardson number state is attractive in some sense, that you not only is it strictly away from the linear stability value, but it attracts solutions. And so to understand whether that attractive situation happens, we need to look at a different kind of continually forced problem, which is the one that Philip looked at. And so we see that what we start off with here, we start off with a buoyancy flow like this and a velocity shear like that, and we require the flow to be relaxed back to those forcings even after as the instabilities develop. And so we see a classic situation that happens that actually, even though we're trying to force it back to the original profiles, the density profile and velocity profile broaden due to sort of these eddies developing. It broadens with time, such like the scale over which the velocity varies and the scale over which the density varies ends up with being the same value, i.e. their ratio remains 1, so it's Kelvin-Helmholtz-like dynamics, but it broadens. And the question is, as it broadens, therefore, that means that the velocity shear gets weaker. And remember, the Richardson number is the density gradient on the top divided by the velocity gradient squared on the bottom. So if they both get weaker by the same amount, you expect the Richardson number to get to have got larger because of the one is squared on the square on the bottom. If it's got smaller, you expect the quantity to get larger. And so here's what happens when you have small Richardson number. You develop into disordered turbulence, and you see this, the shear is going on, you see characteristic scales that develop, but it all looks nicely, largely disordered. But if you start off at higher stratification, this was what we showed at the beginning, something fundamentally different happens. You see the turbulence cannot sustain itself. You see the billows roll up, they break, and then the flow enters this quasi-periodic cycle. It's not able to maintain itself. And so when does that happen? Well, let's look at the Richardson number at the midpoint for 3 different Reynolds numbers. The behavior is largely the same. You'll see when the midpoint Richardson number is less than about 0.1, 0.15, again, you have continued steady turbulence. But if the midpoint Richardson number gets to a larger value than that, you can't sustain the turbulence and you enter this oscillatory state. You inevitably can't remain in that dynamics. So you are attracted towards this gradient Richardson number being about 0.15, but above it, it's terribly intermittent. So is this equilibrium flow relevant? Let's actually look at real oceanographic data. Oceanography took these measurements off Palau, which is in the north of Australia in the Pacific, and they took direct measurements of the dissipation rate epsilon and this mixing rate chi. They took direct measurements in the ocean, and we compartmentalize them into different mixing regimes. Certainly don't have time to talk about that, but I want to show you the actual, we did that, oh, I can't talk about that. We looked at the data in these 5 different kinds of mixing events and worked out what the gamma was. Now, for virtually all the data, well, for 80% of the data, the gamma was about 0.2. It was in this kind of equilibrium state. But the 4th conjecture I want to make is all to do with this tail. Because actually, how have I ordered this data in the horizontal? It is how much actual mixing is associated with each of the events. And you see the ones that have got a lot of mixing. Remember, this is logarithmic, right? So this is 10 to the minus 8 watts per kilogram, whereas this data is 10 to the minus 6 watts per kilogram. And so this is 100 times stronger mixing event than that. And so we found that though virtually all mixing events had gamma 0.2, the ones that were actually doing the mixing that mattered were much, much more efficient. And you see over here, for example, 15% of the points do over 90% of the mixing, and they're much, much more efficient. And so the 4th conjecture is that though the equilibrium state is common and attractive, it actually isn't relevant for shear-driven mixing, and you need to look at the tail events, the extreme events, to understand what's going on. Roberto's turned his camera back on. That means I've overshot my time. And so I'll just put up my conclusions. I wrote an article 6 years ago titled "Open Questions in Turbulent Stratified Mixing: Do We Even Know What We Do Not Know?" And it's still pretty much open things. But what is emerging is those stratified flows have beautiful instabilities. Those instabilities need to be strong enough for you to have a certain amount of mixing, and for you to have sustained mixing, you have to have weak stratification. And when you go over that weak value, you suddenly can't maintain mixing anymore. And even though that equilibrium state clearly exists, it is spatially-temporally intermittent, rare and very efficient and extreme mixing events that really matter. So thank you so much for your attention. I'd happy to answer any question if we've got time. Thank you again for your attention.
Thank you, Professor Caulfield. Okay, let's open the audio and for the audience, please, if somebody need to talk, questions, comments, or whatever, just ask in the microphone or just type in the message in the chat, please. Okay, I have a curiosity before. Okay, I work in control theory. In some sense, there are several PDEs that you have the
Yes.
instability problem, but you just construct feedback laws that you can, in some sense, uh, produce some stability results. Okay.
Yeah.
My question is, in this kind of equation that you presented here, there are several problems related about control theory in this sense.
Oh, yes, yes. So the effectively that thing when we were trying to find the equilibrium was a control theoretic approach.
Mhm.
The and indeed the uh, another side of my life, I should have chosen to talk about that, is really trying to control industrial flows to achieve the objective of maximum or most efficient mixing. And
Right.
so there is a great so it's kind of the inverse of the usual. You want to suppress turbulence and you want to get rid of the instabilities, but you actually want to control the thing to do as much to have as much instability as possible and to
Mhm.
go off. And so I think that we certainly are looking at understanding what is the best way to perturb a flow. I subliminally flashed up a thing saying Goldilocks mixing. We are interested in a situation where the stratification is just right to do and the shear is just right and the perturbation is just right to do the maximum amount of the optimum amount of mixing, and that is entirely a control theoretic question. And indeed, there is also an argument that it is more efficient to use reduced order models rather than the full nonlinear Navier-Stokes equations to actually identify the best approach. And so that is definitely an ongoing area of research, because with my hat on of talking to climate scientists, they want to know the envelope of what's possible. They want to understand, these are going on about these extreme events. They want to understand, well, how likely are those extreme events and when could they happen? Because that's really the way you want to improve the parameterizations in these models, is to actually understand they call them gray swans, right? So it's not that they've not necessarily been seen before, but they can exist, right? And you want to understand what those extreme events could be like. And to understand that, you have to consider reduced models that you control, but control to be as turbulent as possible or as mixing as
Right.
possible.
Right. Okay. Thank you. Thank you very much, Professor. Okay, more questions or comments? The audience can write in the chat or just open the audio. If not, thank you, Professor
Thank
Caulfield,
you
for the
very much for
nice,
your attention.
beautiful talk.
Okay, cheers. Thank you very
Cheers.
much again. All the best. Bye bye.
Thank